So far we have studied two different ways of biasing a transistor and then realizing common source amplifiers using those biasing schemes. Now we will continue our exploration of different ways of biasing. We will continue with what we started, that is sensing the current difference at the drain and feeding back to the gate. Okay, and then see another alternative by which we can realize a common source amplifier. So when we sense at the drain and feedback to the gate, we have a MOS transistor with the source, let's say, connected to ground. It's connected to a fixed voltage. When we say feedback to the gate, the idea is that the source side is fixed and gate is variable. It's based on feedback. Then by connecting a current source I0 to the drain of the transistor, we have a situation where the difference I0 minus ID tends to flow that way. Okay, and we can imagine that there is a parasitic capacitor into which this current is flowing, and that's a good way of visualizing things. It tells you exactly what happens when I0 is more than ID or less than ID. Okay, and if I0 is more than ID, this voltage tends to increase. Now to increase ID, we want the gate voltage to increase. So in general, the drain voltage is varying in the same sense that we want the gate voltage to vary. Okay, so we can connect the drain to the gate and complete the feedback network. Okay, and this will in steady state ensure that ID equals I0. Okay, the gate voltage will get adjusted to the threshold voltage plus 2 times I0 by mu n Cox W by L. That is, it's exactly like varying the gate voltage until the current in the MOS transistor becomes exactly equal to I0. Then any variation here will stop. Now this is not the only possibility. We can also have any other block here. Okay, I will just show it like that, indicating that this side is the input and that side is the output of whatever is shown as the triangle. Okay, so what must happen is the following: I0 minus ID. So if ID is smaller than I0, VD increases. Also, if ID is smaller than I0, VG must increase to make ID closer to I0. Okay, so putting these two together, we see that our sense of the current difference, which is the voltage here, if it increases, VG must increase. Okay, so it's not necessary that VG be equal to VD like here. All we want is that the gate voltage must increase when the drain voltage increases. So we can complete it through an amplifier or any other device. In fact, in the assignment and in activity questions, you have seen examples where this is not a direct connection like that, but you could have a fixed voltage drop. Okay, in either direction, it doesn't matter. Because now if this side increases, this voltage is fixed, that side also increases. Okay, and it doesn't even have to be a simple voltage source like this. It could even be another amplifier or something. All we want is that the output voltage must increase when the input voltage increases. Okay, so VG must increase when VD increases. So this basically means that this amplifier must have a positive incremental gain. It's not even necessary for this block to be linear. Okay, as long as the output increases as the input increases, it's fine. Okay, the output input characteristic could be anything. So this here, I am sketching the output input characteristic of this amplifier or that device, whatever it is, and it could be a straight line like that, it could be offset from being a straight line, or it could have a shape like that or like that. Anything is possible. Okay, so this leads to a huge variety of ways of actually completing the feedback around it. And like I've been emphasizing repeatedly, the only way is to understand the logic. because sometimes what is in this could be quite complicated. Okay, so that you understand exactly how the biasing is done. Now let's see other possibilities of realizing common source amplifier using this kind of bias. Okay, let me redraw this with the MOS transistor turned this way. Okay, now I said that if you make many transistors, they will all have different characteristics like threshold voltage, current factor, and so on, and also these characteristics vary substantially with temperature. Now it turns out that if you make two transistors close to each other on an integrated circuit, okay, the integrated circuit is at the heart of all of our electronics today. So it's a small piece of silicon on which number of transistors are fabricated, numbering in the billions. But let's say you have two transistors right next to each other in such a chip. Okay, first of all, the processing happens together in the same machine under very highly controlled conditions. So the processing steps for the two transistors will be exactly the same. And also because they are on the same chip, okay, and very close to each other, they are not likely to be at very different temperatures. Okay, so on a chip, if you have two closely spaced transistors, then their characteristics will be nearly identical. There will be slight differences, but the differences will be much smaller than if you take two separate individually packaged transistors. Okay, so in such circumstances, especially in integrated circuit design, it is useful to rely on two devices having identical characteristics. In fact, a lot of IC design, it turns out, is done this way. Okay, it turns out on an integrated circuit, whether you make resistors or capacitors or transistors, their absolute values may not be very accurate. That is, if you try to realize a 10 kilo ohm resistor, it could be anywhere between 8 kilo ohms and 12 kilo ohms. But it so happens that if you make two identical structures, both of which have to be nominally 10 kilo ohms, one of them is 8 kilo ohm, the other one will also be 8 kilo ohm. It will be very close to the other one. If you make two identical structures, they will have identical resistances, although the exact resistance value may not be known. Okay, so the same goes for capacitors and transistors. So a lot of IC design is done by exploiting matching properties of transistors on an integrated circuit. Now let's assume that we are in such a context. So far we didn't use this. Okay, we had only one transistor in the circuit. Now let's say we have multiple transistors and all of them are matched. Then let me take another transistor. Let me call this M0, M1, and I'll say M0 equals M1, meaning that they are well matched. Okay, that is, they're also on the same chip so that their temperatures are the same and so on. So now the VGS of M0 is such that a current I0 flows in M0. For now, let's ignore the dependence of the drain current on the drain source voltage. Okay, the saturation drain current depends only on the gate source voltage. That's our assumption for now. In that case, if we apply this VGS to a transistor which is identical, then bias transistor M1. This is just to show that there is some VDS more than VGS minus VT. Okay, it doesn't have to be a voltage source. You could connect any other circuit to this point. Just make sure that the drain voltage is more than the gate voltage minus VT. Okay, if you do that, then the current flowing here has to be equal to I0. Okay, so I hope that part is clear, because the VGS value here is VT plus square root 2 I0 by mu1 Cox W by L, that is set by negative feedback. And if this VGS is applied to another transistor, the current in that will be mu1 Cox W by L divided by 2 times VGS minus VT squared, and that will be equal to I0. Okay, it turns out that this is a very interesting and useful circuit. If you apply a current I0 to this transistor, you can replicate it in another transistor. Okay, so M1 is also biased at a constant current I0. And this is very useful for several reasons. First is that you can make several copies of the current. Okay, now I don't have to stop here. I could, for instance, have another M2 which is also identical to this, and if it is biased in saturation, then the current here will also be equal to I0. Okay, so I can make any number of copies of the current. Okay, and there is no limit to how many devices I can connect, because these gates of MOS transistors, they do not draw any current. That is, they do not load whatever they are connected to. So I can connect even 100 devices here and I'll have 100 copies of this current. Okay, and this such a structure where you establish the gate source voltage of one transistor using negative feedback and replicate that voltage on all other transistors. That's known as a current mirror. Specifically, you can mirror it to a number of devices, but typically this structure with two devices, this is known as a current mirror. Okay, and it's a very widely used block in integrated circuit design because you can replicate currents like this. Now it turns out that you can also scale the value of the current. Okay, for instance, let's say that I didn't want I0, but I wanted 2 times I0. One obvious way to realize that is by taking 2 of these copies and connecting them together. Okay, so for instance, I can take this voltage, replicate it on replicate the VGS on 2 transistors and connect them together, where M3 and M4 are all identical to M0. Okay, here we will get 2I0, assuming that these are in saturation. Okay, so you can even get multiples of a current or submultiples of a current. And another way to think about this is that I replicate it on an identical device, M5, but the difference is that, let's say M0 has a width of W and a length of L, then M5 will have a width of 2W and a length of L. Again, using this value of VGS applied to M5 and using the current equation for M5 in saturation region, you will find that the current flowing in here is 2I0. So by scaling the width of the transistor, you can also scale the current, and there is really no difference between the two. You can think of tying multiple devices together as scaling the width by an integer factor. Okay, so at this level of the course, this much is enough, that connecting transistors in parallel is the same as scaling the width. Okay, so this current mirror can not only replicate the current, it can also scale it. Okay, and this is a very important circuit because later we will see that the preferred way of biasing all transistors is to bias them at a constant current instead of constant VGS. So that means that for biasing every transistor, you need a current source of that value I0. Okay, where do these current sources come from? We have not yet discussed how to make a current source, but at least now we know that if we have one current source, we can create multiple current sources of scaled values. Okay, so this current mirror is a very useful block in that sense. Okay, and we can also bias a transistor which is being used for an amplifier in the form of a current mirror. That we will see in the forthcoming lessons. Okay, so hopefully the concept of current mirror is clear. It requires matched devices. On one of the devices, you establish the VGS using negative feedback by comparing the drain current with the desired drain current and feeding back to the gate of the transistor. And you replicate that VGS on all of them. They will all have the same currents, assuming they are in saturation region. Of course, there will be small differences because the drain current does depend on the drain source voltage. Okay, there is that 1 plus lambda VDS factor. So if the VDS of M1 is different from VDS of M0, the actual current will be slightly different, but for now we will ignore all those differences. Okay, in practice you may have to take into account those things as well, depending on the level of accuracy that you want. Okay.